Hi everyone. In this video I'm going over 3.3 differentiation rules. Don't worry about this writing at the top. This was for something else. So looking here, it says in 3.2 we worked on the following problem. So we were looking for a formula for the derivative. So we were just leaving the derivative as a function of x of this cubic function, x cubed. Example 5, example 5, it was actually part 1, really. It's actually right here. So it's actually example 5, part 1. So that should have been just part 1, actually. So, and on that page, you can see it here, I retyped it. But we used the definition. So we went through the definition, applied it accordingly, and eventually got this as our derivative. So again, that was, we applied this definition, and that eventually amounted to this derivative here. So in 3.3, we're going to learn that we don't need to do the definition every time. And really going forward, from a certain point, unless you're being asked specifically to use the definition, you're going to be free just to take derivatives this more direct way, which we're about to learn here. Okay, so yeah, we went through, we got this, but maybe there's a different way, right? Because what if our function were x to the 50th? Right, let me just explore that here for a second. So if we had x to the 50th, then the derivative of that function would be the limit as h goes to 0 of x plus h squared, to the 50th, minus x to the 50th over h. And it's really a problem now because we have a power of 50 rather than what I accidentally wrote, like a square or something more user-friendly, right? This 50th now would require maybe some other way of factoring. We want to factor this out traditionally, right? So what about cases like this? We don't really want to use the definition here, and that's the point. So is there a shortcut? Yes. If you just kind of look at what we had and what we ended up with. So here's what we ended up with. Here's what we started with. So what if we just took that 3 and moved it down and then reduced that 3 by 1? So that's essentially what happened, right? That 3, there's now a 3 out front. And then instead of being x cubed as it was, it's now just x squared. And that's exactly what you would do. Really going forward, to take the derivative of this x cubed, this polynomial here, I would just bring down this 3 and then reduce the power on x by 1. And there's a formula for that. And I have it for you right here. There is a little typo in here. So there should be a prime. So we denote these derivatives with these prime. It's almost like an apostrophe, but we call it a prime. So that denotes the first derivative of f. So I should have had a prime notation right here for the derivative. So just to write it again in general. So the statement is if f of x is, let's just say x to the n, then f prime of x, its derivative, will be n times x raised to the n minus 1 now. So that's called the power rule. And that's another way of saying it here. So I'll talk about this notation. So you'll see this piece, which I don't know that we've seen this operator yet. So this is a differential operator. And it basically tells you that you're operating on some object. And it's specifically telling you that the operation that you're using is the derivative. So it's saying, this is basically math's way of saying, I'm taking the derivative of x to the n with respect to x. And this is the result. Okay. So this is called a differential operator. And it's like a call to action, basically. And this action happens to be the derivative. Okay, here are some rules. It says the derivative of a constant is 0. Keep in mind the derivative is a measure of slope. So imagine you had this constant function. Let's just call this the function y equals c. So if that's a horizontal line through C, then what would be the slope of that horizontal line at any location x? Right? The slope of this horizontal line at any location x would be 0. So keep in mind there's a very, very strong connection between this derivative and a measure of a graph's slope. Right? So if we're measuring the slope of this constant function, the slope is 0. Here are some rules regarding like the algebra of the differential operator. So we have, if you're taking the derivative of a constant times a function that you care about, well, you can actually move that constant out front and then just focus on taking the derivative of the function and then multiplying afterwards. So it's not like C just disappears. You're allowed to move the differential operator inside of that multiplication so that it can operate on this thing that involves x. If you have functions f and g and you're adding them together and you want to take the derivative of that sum, you can actually pass the derivative operator, kind of like distributing it to each function, take those derivatives and then add afterwards. So the derivative of a sum is the sum of derivatives. If you have a difference, so the derivative of a difference can be written as the difference of derivatives. So you're going to get a lot of practice at using these. Yes, you need to know all of these, but really they're going to be so often used that I don't know if you'll have a choice in knowing them or not. So example 8, all right, I'm going to do all these ones, I think in blue. Yeah, blue. So this function, it says differentiate the function. All right, so I'm supposed to find the derivative of this, and it's 3 to the 19th. What type of function is that? That's this type, right? It's a constant function. Even though it's a very, very large constant, it's still a constant. So f prime of x would be 0. Right? If you wanted to show a little more work, you could say f prime of x equals this derivative of 3 to the 19th. And then you could say, okay, now that's 0. All right, next page. Part 2, page 35. F of t. So if I want f prime of t, then that'll be d dt of this function here. So I'm not actually taking the derivative yet, but I'm just saying, hey, notationally, it's not always x, right? It's whatever variable is involved. So if we have t's going on here, it'll be d dt, telling us we're differentiating with respect to t and not x. So I'll need to pass the derivative operator to every term. So if I want to show a bit of work, I'll go ahead and do that here. So I would say d dt of this first term. So what I'm doing here is kind of a combination of these two, the sum and the difference. So I'm just trying to show a lot of work. This is not what we're going to do really in practice as we go forward. And then minus d dt of 2/3 t squared. And so on, minus d dt of t plus d dt of 10. So now, writing this, so the derivative with respect to t, again, I could now go ahead and move the derivative operator past the constant, right? So I could write another step. I'm not going to do that. I'm going to go ahead and take the derivative now. So we multiply down. So we always multiply down here. So I'll get now a 10t, and then I reduce that power on t by 1. So I'll have 10t to the 4th for that term. And then it'll be minus 2 times 2/3. So that'll be 4/3. Again, I'm taking this power rule. Right, the 2 here is multiplying by the 2/3. I get 4/3. And then reduce the power on the t by 1. I just have a t now. There's technically a 1 up here. So if I multiply down, I would have minus 1. Right, I'll just go ahead and write it. 1, and then times t, and then 1 minus 1. So I'll just show a lot of work there. The derivative of a constant is 0. So finally, I'll go ahead and write it as 10t to the 4th minus 4/3 t minus 1. Let's try another one, part 4. So for p prime, so we would have p prime of z. And just to introduce the notation again, this would technically be d dz of this expression that were originally given. Okay, so now to actually take the derivative, I would theoretically need to kind of pass this operator to every term. But in the spirit of saving a little time, I'll just go ahead and write down what we get. So we multiply down and then reduce the power by 1. Okay, so multiply down by -2, we get -6. Z, reduce the power by 1, and we actually have -3 now. Multiply down by -1/2. So I'd have -1/2 times z, reduce the power by 1, right? Subtract 2 halves essentially. So -3 halves. And derivative of a constant is 0. So if you need your exponents to be positive, you would want to write -6 over z cubed minus I guess we'll say 1 over 2z to the 3/2. So this would be the with positive exponents version here. Okay, moving on. All right, so yeah, here's a physics related problem. So the derivative can do a lot of cool things for you as far as kinematic equations and connecting acceleration to position and velocity and all those equations of motion. So what we're going to see here is we have a motion equation or a position equation. So it says the equation of motion of a particle is given by this cubic, where s is in meters and t is in seconds. Okay? So this thing says if you tell me a number of seconds, I'll tell you the position, so the distance from some beginning point a particle is. Okay? So part 1 says find the velocity and acceleration as functions of time. So if you have position and then you take the derivative, what you'll then have is actually a velocity function. So if you start with a position function and then you differentiate, meaning you take its derivative, you actually now no longer have a position function, you now have a velocity function. If you take another derivative, then you'll have an acceleration function actually. So this is our connection between these different quantities we often care about. Later on, we'll learn how to go this direction. That'll be the integral. That's later. So to go ahead and do that, we have s is our position function. So I'm going to differentiate to get the velocity function. And then I'll just leave it in terms of t. So s prime of t, I'll use the power rule. And that would be the velocity. The acceleration would simply be the derivative of the derivative. So we sometimes call that s double prime. So if I am taking the derivative of a derivative, we can just tag another one of these primes on there. So again, the power rule, multiply down, I get a 6t minus 6, it looks like. That's part 1. Part 2 says find the acceleration after 1 second. So I would be looking for s double prime of 1. So it looks like 0. And that would be in terms of meters per second squared, actually. Those are the units on acceleration in this case. Part 3 says find the acceleration when the velocity is 0. So here's our velocity function. I'm going to go back to it and set it equal to 0. Okay, so going ahead and doing that, solving this equation here, so opposite of b, plus and minus the square root of b squared minus 4 times a times c, quadratic formula here. And I'll go ahead and type that in. Okay, so here's my kind of t plus, if you will. So t plus, just because it was the plus case, is 3 plus root 3 over 3. And then if I just go back, press left, right? Just use this button a bunch of times, and you can delete that plus, replace it with a subtract, and do the minus case. So I'll say t minus is 3 minus root 3 over 3. Okay, so we have these conjugate pairs. Let me see what number this is. This is 0.422, okay. Just making sure that we don't have negative times. And then for the other one, of course we don't have a negative time there. So these will be our times. So it said find the acceleration when the velocity is 0. These two times are when the velocity is 0. So I need to evaluate the acceleration function now at these two times. So I'll have s double prime of 3 minus root 3 over 3. So this will be the t minus 1. Okay, let me type that back in. Okay, so now plugging this back into here, right, our acceleration function. So 6 times, and then I can use answer, minus 6. So I get negative 2 root 3. So we have a negative acceleration there. And this would be meters per second squared. And then s double prime of 3 plus root 3 over 3. So 6 times 3 plus root 3 over 3. And then minus 6. So positive. Okay. There's example 9. So there are other functions out there. So you will need other tools to differentiate those functions with. Right, what we've seen so far are polynomial kind of sum and difference of different polynomial terms and differentiating those. And you can get by with that a lot. In other cases, you'll need different rules. And this is the first of a different rule we are going to need in certain cases. It's called the product rule. So here it says the derivative of this product of functions is this. Okay, so let's identify what this is saying. It's saying to differentiate this product of functions, what you need to do is actually just leave the first function as it was, and then multiply, so there's a multiply here, by the derivative of the second. And that's the first term, but then it says go on to do an additional term where you kind of do the opposite. You leave the second function undifferentiated and you differentiate the first. So kind of a summary of that. If you want d dx of f times g, let's say, just to keep it a little more simple, you can say f times g prime, right? Just f times g prime. This is g prime right here. Plus g times f prime. Just to keep it a little more simple as far as the language goes. This is what's on the right. Okay. Let's try one. So example 10, here we have a function f, so that's maybe confusing. Let me change this to a function h, okay? Let's say we have a function h of x, which is equal to x squared times 1 plus 2x. So that'll allow me to use f now. So I'm going to call this one actually f. And then I'll call this one here g, just so we can match up a little bit better with what's written right there. So to find h prime, in other words, to differentiate, this thing says to leave f as it was, so I'll just write x squared, but then we need to multiply by the derivative of g. Here's g, its derivative. So if we just forget about f for a second, just take this derivative now, 0 plus 2. So that would just be 2. Okay, so that's this term. And then we add kind of the opposite situation. So now I'm going to take g, just as it was, and then multiply by f prime, which in this case is 2x. So this is the derivative. And now we just probably want to simplify it a bit. So h prime of x equals 2x squared. And then if I distribute this here, I'll have plus 2x plus 4x squared. And then ultimately I can combine like terms, 6x squared plus 2x would be its derivative. Notice though you can, in this case, get around the product rule. We could have distributed and then taken the derivative. So, all right, let's see another one. Okay, this is page 37, by the way, example 12. I'm skipping past a couple of these. Of course, I'll post solutions to all of them next to the video. I am likely just going to do f single prime on this one, actually. So check out the key, perhaps, for the other part. I'll just do f single prime. So as I was saying, you can do a little bit of algebra first. So f is the exact same as, maybe I'll just rewrite it as x to the 1/3 power, right? Cube root, same as 1/3. And for differentiating purposes, it's nice to have powers instead of roots. So another x to the 1/3 times x squared, that means I need to take 1/3 and add 2. This is my power now on x. So this will be plus x to the 7/3. Okay, so this is just f. This is not the derivative. And now I can go ahead and say, okay, let's take its derivative. I would have had to use the product rule, but I can sidestep it here. So power rule now is the only thing I need to do. Reduce 1/3 by 1. So that's negative 2/3. Multiply down. So I get 7/3 x reduced by 3/3. We get 4/3. It is good to factor these, so you may want to leave these in factored form. Eventually, it'll be nice to have them factored, so it's a good habit to begin thinking about. So I'll factor out maybe a 1/3 times x to the negative 2/3, and then that would leave behind a 1 plus 7x squared. Yeah. So coming up pretty soon, we'll be wanting to set our derivatives to 0, not right now, but in a little bit, you're going to want the factored form, is what I'm saying. So, good thing to start to think about. Okay, another rule. So that's been the kind of product rule, the power rule. There's also a quotient rule. So let's see this one. This one's saying if you have not a product, but a quotient of functions. So if you have a function over another function and you want to take that derivative, this is how you do that here. Okay, so I'll break it down a little more simply. So d dx, if you have f over g. Sometimes all these differential operators get a little confusing to look at. So I'll just say g times f prime, right? G f prime minus f times g prime over actually just g squared. So it's not the derivative of g, but it's just g squared. Okay, so I kind of want to change this one to h as well. I'll do capital H this time. So let's say we have capital H of x equals this thing. So this is playing the role of f, this is playing the role of g. So to find h prime of x, then this says to multiply by the bottom, right? This is g, so I'll just take it, and then times the derivative of the top. Okay, there's the derivative of the top there. And then I have to subtract the top, unchanged, times the derivative of the bottom. And then everything is divided by the bottom squared. Okay. I'll go ahead and simplify and maybe just clean the result up a bit. So go ahead and distribute. So we'll have 12x cubed plus 3x squared. Do some distribution of the negative and the 4. So minus 4x cubed plus 8 over 4x plus 1 squared. Maybe combine like terms, and that looks like it actually. Nothing really that magical happens here. We have 8x cubed, it looks like, plus 3x squared plus 8 over 4x plus 1 squared. That is the derivative of what we had originally. Okay, so another rule, quotient rule. So you have power rule, product, and quotient right now. Whoa. Just to summarize. All right. Let's see. Yeah, this one can be tough to visualize. I'm going to do this just with calculus and algebra on the page here, and then I'll bring up Desmos for the end of this video and try to show you the visual here, because I think really emphasizing the picture of this problem is a way of really helping to make sense out of it. This says find equations of the tangent lines to the curve. We have x minus 1 over x plus 1 that are parallel to this line. Okay, so keep in mind derivative. I'll just use equals, but even this symbol means more. It's like defined as, but the derivative really is defined as slope. Keep that forefront in your mind. Okay, so if we want equations of tangent lines to this curve that are parallel to this line, then that means we want the derivative of this curve, in other words, the slope, to match the slope of this line. Okay, so what is the slope of this line? Let's start there. So if I subtract over x, we'll have negative 2y equals negative x plus 2. Divide by negative 2, and we have y equals 1/2 x minus 1, right? So this line, the given line, has a slope of 1/2. So what I want to do then is find y prime and set it equal, force it to be 1/2, and look for x locations for which that is true. Okay, so I need this y prime part, which means I need to take this derivative, which looks like I'll need to go ahead and use that quotient rule. So y prime, one way to remember it, there's this little phrase, you can say low d high minus high d low, square the bottom and away you go. So low d high, meaning just keep the low one, and then the derivative of the high one. Minus, so the phrase again, low d high minus high d low. So here's low d high minus high d low. Square the bottom and away you go. So this is its derivative using the quotient rule. But now, as I said, we want to force or search for when that derivative is parallel, meaning the same, to the slope of the given line. So I'll simplify this a bit. So it looks like we'll have just x plus 1 minus x plus 1 over x plus 1 all squared, right? Some simplifying. So we'll have 1/2 equals, it looks like the x's cancel. And I have 2 up top over x plus 1 squared. Okay, maybe cross multiply at that step. So in other words, we'll have x plus 1 squared equals 4. So basically I took this times that and this times that. And now square root property, plus and minus on the side with the number. So these cancel, and we have x plus 1 equals plus and minus 2. Subtract. So I'm getting x equals negative 1 plus and minus 2. In other words, we have an x location of 1 and an x location of negative 3 for the locations at which the tangent line to the given curve is parallel to the given line. Okay, so we just found the x locations for which this is happening. What we need are also the y locations. This thing tells you y locations based on x locations. Okay? So there's going to be 2 equations. So let's find y1. So I'm going to plug in x1 here to find y1. So y1 will be 1 minus 1, right? I'm plugging this into y over 1 plus 1. So we have 0. So in other words, we have a point of 1, 0. I'll just notate it that way. And then for -3, that'll be y2. We have -3 minus 1 over -3 plus 1. So we have -4 over -2. This is 2. So we have another point at which this occurs of -3, 2. Okay, so I have points that I know are on my lines, and I know that I want my lines to have a slope of 1/2. So I can go ahead and write them now. So I would have y minus 0 equals 1/2 times x minus 1. That's using the first point in point slope form. And then I would have y minus 2 equals 1/2 x plus 3 in point slope form. And in slope intercept form, and that's how I'll leave it actually, I'll write this in a different color. We'd have y equals 1/2 x plus 7/2. That's actually the second one. And then we would have y equals 1/2 minus 1/2. 1/2 x minus 1/2. Okay, so that's kind of the calculus algebra behind it. It's hard to visualize maybe. I'm going to bring up Desmos now, try to explain us through that. Okay, I'm going to type in the one we just did on page 39. Example 14, we found those two tangent lines, but as I was saying, it's kind of difficult sometimes to visualize this. I'll type in y. So there's the given function. I'll type in the given line. So x minus 2, y equals 2. So there's our given line. So just to kind of set up the problem, we're looking for a line, or sorry, two lines that are tangent to our given red curve, but not only tangent to the given curve as what I'm trying to do here on the upper one with this edge, but not only are they tangent to that curve, but they're parallel to this given line here. So you can see like right around here, if you look at the upper edge of my ruler, it's tangent to that red curve roughly, and it's also roughly parallel to the given line. And luckily, as I sit there, also you can see the bottom red curve, the other edge of the ruler is kind of tangent to it and also parallel to the blue line. The lines that we found, so y equals 1/2 x plus 7/2, and then y equals 1/2 x minus 1/2. So you can see this green one that popped up, it is tangent, right? It hits exactly once, and it also shares the slope of this blue line. And then this purple line is tangent to the given curve in red, and it is parallel to the given blue line. Okay, so that's kind of the picture of the problem there. All right, talk to you next time. Bye-bye.